Okay, so let's continue on with our RLC circuits, in particular our series RLC circuit, and we'll start parallel RLC circuits today. So here's a first example just to refresh what we did the last lecture. Find I, which is, well, actually it's find total current, or there's only one current in this circuit because it's series, and find voltage across the resistor, inductor, capacitor at resonance. So first I thought, oh, find resonance, but I didn't have to find resonance because it's already at resonance, because XL and XC are equal, so that means we are already at resonance. To find I total then, XL and XC will cancel each other out at resonance, and we have only R, so I will equal V source over R, because the ohms here and here can't, XL and XC will cancel each other out. So that's 0.05 volts divided by 22 ohms, and that is 2.27 milliamps. So now find VR, VL, and VC. So it's still application of Ohm's law. So VR equals I times R. There's one and only R in the circuit. So it is our 22 ohms times 2.27 milliamps, which will end up being 50 millivolts. V in the across the inductor is I, there's only one and only I, times XL, which is 100 ohms already given to us. So it's 2.27 milliamps times XL, which is 100 ohms, which is 227 millivolts. Yes, and since XC is the same, it's 100 ohms, VC is I times XC, and you will get the same answer because it's still 100 ohms, and it will also be 227 millivolts. So 227 millivolts and 227 millivolts here, and VR has 50 millivolts here, and V source was 50 millivolts. So what do you notice? That V source and VR have the same voltage across it. So V source equals VR at the resonant frequency, and L equals VC at the resonant frequency. But what are those values? They're huge, 227 millivolts each, but they are out of phase with each other. So if I were to be able to draw that, I would have VR doing something like this, and I would have VC doing something like this, and VR and VC would cancel each other out in the circuit, and VR, not VR, VL and VC would cancel each other out at this resonant frequency, and all of the voltage of the source would be across the resistor. Not to say that these two guys don't have voltage across that. Always keep it in mind. It may be resonant, but there are some big voltages across each one of those devices. They're just out of phase with each other, so the voltages will cancel, but they do exist if you were to measure them individually. So as I've actually conveyed in the previous lecture, if you were to compute the Z total as a function of frequency, so as frequency changes, remember we have XL doing this 1 over F kind of shape right here. Maybe I'll do this. XC is doing this 1 over F kind of a shape, and XL is doing this straight line shape. Because why? Because XC equals 1 over 2 pi FC, so we have a 1 over F shape, and XL has a 2 pi FL shape, which is just a straight line passing through the zero, passing through the origin right there. And then you add, and then you compute Z then you compute x total, which is the absolute value of xc minus xl, and that's what the last line here represents. This line right here is that x total. X total is right here. And it gets that kind of a shape. So at resonance, z total is at a minimum, and z total equals r at resonance. And at all other frequencies off resonance, the total impedance of the circuit is greater than it is at resonance. So z total is a larger number, means less current. Here it's capacitive on this side, because xc is greater than xl, and on this above resonance it's an inductive circuit. So this is just an exercise. Determine the resonant frequency or determine the impedance at the resonant frequency at 1 kilohertz above and at 1 kilohertz below. So I think we could probably do that pretty straightforwardly. Interesting thing about this problem, though, is it did not give me the resonant frequency, did it? So let's find this resonant frequency. What is it? Fr equals 1 over 2 pi square root of L times C. So we can find the resonant frequency. Well, plug in the numbers, and I will get 5.03 kHz. That's the resonant frequency. And then F resonant minus 1 kHz. Oh, what is the impedance at resonance? At resonance, Z equals what? Just equals R at resonance. So at the resonant frequency minus 1 kHz is 4.03 kHz. Then you have to find xc, which is 1 over 2 pi fc, 1 over 2 pi 4030 hertz times c, 0.01 times 10 to the minus 6 farads. I compute it, and I will get 3.95 k ohms. That's xc. XL will be 2 pi FL, which equals 2 times pi times 4030 hertz times L, which is 0.1 Henry. I do that math, and I will get 2.53 k ohms. So XC is bigger than XL. At 1 kilohertz below the resonant frequency, we expected the circuit to be capacitive. It truly is capacitive. So we can find X total, absolute value of XC minus XL, subtract the two, and we will get 1.42 k ohms. And we can find Z. Z equals square root of R squared plus X total squared. And when I do that, I get 1.42 k ohms again, coincidentally. So, and you do the same thing above the resonant frequency. You can make the calculations again, and you'll just get new numbers, but you will see that above the resonant frequency, it's an inductive circuit. So above the resonant frequency would be at 6.03 k ohms, at 6.03 kHz. At that frequency, I'll just give you the answers. XC would be 2.64 k ohms. XL will be 3.79 k ohms. Yes, indeed, it's now an inductive circuit. X total, absolute value of XC minus XL. Oops, absolute value. It will be 1.15 k ohms. So one of the things to note about that, X total below was 1.42, 1 kilohertz below was 1.42 kilohertz, and X total above resonant frequency was 1.15 kilohertz. So it's not a perfectly symmetric behavior about the resonant frequency, which is how earlier I had a slide that showed that earlier right here. What's in terms of voltages, but it shows this kind of a uneven shaped plot for what the voltages are doing, and what here's voltage across the capacitor, here's voltage across the inductor, and they don't really look like an even shape, which is part of the reason why it comes about, because the reactances calculate to be different values above and below the resonant frequency. So, and then you can compute the phase angle in each one of these cases too, and when you're at the resonant frequency, the phase angle is 0, but it turns out that above the resonant frequency, when you are inductive, the phase angle is actually a positive angle, because we are putting ourselves, this is VR. If we end up with an inductive circuit, we have V across the C and L being that way, and then we would have V source here. So when it's inductive, you have this would be a positive phase angle, but when you get the opposite case going down into this quadrant down here, if you had a capacitive circuit, then the phase angle actually goes negative. So why have we studied all of these circuits, or all this particular circuit, and what's it good for? That's probably the ultimate thing. What's it good for? He did figure out that an RC circuit has some filtering properties, and so does an RL circuit. But what about an RLC circuit? What is it good for? So depends again where you take the output, what part of the circuit you take the output from. Remember when we had an RC circuit, if you took the output out from the capacitor, it was a low pass filter, but if you took the output voltage from across the resistor, it was a high pass filter. So what does an RLC circuit do? Well, if you take the output voltage to be across the resistor, so I put my input AC over here, and then I put my output oscilloscope or whatever I'm measuring across the resistor, what is the behavior of the circuit? Well, it turns out it becomes what's called a band pass filter. So this is what a band pass filter shape generically looks like. This is frequency on the, frequency is on the horizontal axis. The resonant frequency is right here, and remember at the resonant frequency we have maximum current. So resonant frequency has maximum current, but below the resonant frequency the current is less because the total impedance in the circuit is higher. And so there's this pass band shown right here by bandwidth. There's this pass band right here that where the frequencies can get through, and if I'm way past the resonant frequency, the circuit won't let very much voltage get out at all. So if I'm measuring across the resistor, not very much voltage will come out if I'm way past the resonant frequency. So this is a very important application, and so it's given some attention and some special terminology. So if I look at the voltage or the current where it's maximum, which is at resonant frequency right here, and I go down to where, let's say the maximum V out is 1 volt. Let's pretend it's 1 volt. If I go to where the voltage is down by 0.707, there's that magic 0.707. So I'm at 0.707 volts below the resonant frequency, and I'm at some frequency above where the voltage is now 0.707 volts again. This part of these frequencies right here determine what's called the bandwidth of the filter, or the pass band of the filter. So these frequencies generally pass with the maximum amount of voltage possible. and then the frequencies above and below, these special points called F1 and F2, they get attenuated or reduced in their amplitude. These are called 3 dB frequencies, so I'm going to introduce the concept of a decibel right now, which we call a dB. So if 0.707 is a rounded off number, so 0.707 actually equals 1 over square root of 2. Check it in your calculator. We use 0.707 a lot just because it's easier than typing 1 divided by square root of 2, but the 0.707 is actually 1 divided by square root of 2. This is voltage. So we look at the voltage being down to 0.707 of the maximum. So what is power? Power is V squared over R. Power is also I squared R. Remember Watt's law? So if I say my voltage, let's say my voltage is now 0.707 volts, 707, and I square that divided by R, I get 1 over square root of 2 squared divided by R. Remember, I'm calculating power right now. And so that becomes 1/2 divided by R, which becomes 1/2 times 1 over R. So really, I've cut the power in half, because if this voltage was at the maximum right here at 1 volt, power would have been 1 over R. But at the place where the voltage comes down to 0.707, the power is now 1/2. So that's how people determine what the passband of the filter is, or the bandwidth of the filter is. It's the place where the power is cut in half. And that calculation I just did works the same for voltage or for current, because both times you're squaring 1 over square root of 2 and you'll get 1/2. So the filter bandwidth is also often called half power bandwidth of the filter, and the frequencies at which the power is at 1/2 or the voltage is at 0.707 are called the 3 dB frequencies. So there's F1 and F2. Sometimes they're written F low. Many times on data sheets they're written F low and F high. So that's and then F2 minus F1 gives me the bandwidth, written oftentimes with just as a BW, gives me the bandwidth of the filter. So another aspect of this, so introduce a little bit more math here, is that this half power point is also called a 3 dB frequency. And to understand what a 3 dB frequency is, you have to understand what a dB is, or a decibel unit. So dBs are where you take some number, a ratio, and you find the log of it, and there's a log function on your calculator, a log of it, and then this is a scaling factor that makes the numbers nicer. So a dB is defined as 10 log of the ratio power out over power in, and if you're doing voltage, a dB is 20 log V out over V in. So if I go back for a moment on this circuit, here's our V out right here, and here's our V in, and the 3 dB frequencies are the frequency at which V out over V in. So I find that ratio, calculate that on my calculator, find the log of that ratio on my calculator, and then I multiply it. This is voltage, so I'll multiply it times 20, and if V 20 log, if V out was 0.707 and V in was 1 volt, I would calculate this, and it would come out to be, actually comes out to be minus 3 dB, because it's called the minus because it's lower than the maximum. This is less than 1. So the power or the voltage is down by 3 dB at some particular frequency. You can do the same thing with power. If I calculated power out, and you can calculate power out because it's I times V, because it's I squared over I squared R, or because it's V squared over R, whichever way you calculate it, and you can calculate your power in. And if at some output power is halfway down, some frequency the output power is halfway down, I would say 10 log of 1/2 over 1, because input power was 1, output power is down by 1/2. So I could actually say 1/2 of P in and 1 P in. I calculate that ratio and I'll get 3 dB. Negative because this point is 3 dB lower than the maximum. So those are what dBs do, and I think we need to have an example here. We'll have an example in a moment. So frequencies at the resonant frequency are passed with amplitudes no less than 70% of the maximum. Frequencies outside the pass band are reduced to less than 70% of the maximum and are called the rejected frequencies. They're not totally rejected, they're just reduced in size. Way out here somewhere they are probably totally rejected. Frequencies in the pass band between F1 and F2 are assumed to be passed. Sometimes we say it equally. They're really not equally. So an ideal shape of a filter is a block like that frequencies in this pass band are passed and frequencies outside this pass band are not passed. But you see in the real world that it's not a block shaped filter like that. I should probably do a few examples here before I jump into this other example about Q. So let me, maybe I could just move this down. So I want to show a few more examples of dBs because I think you have a homework problem where you have to calculate dBs. So I'm just going to make up a few problems. Let's say that the power out at 1 kHz of a RLC passband filter. Let's say at 1 kHz the power out is 10 milliwatts, and the power out at, let's say, 500 Hertz equals 2 milliwatts. So if I were to draw a picture, I have 1 kHz right here, and I'm outputting 10 milliwatts right here. And I know it's some kind of a passband filter that's occurring, but I'm saying that at 500 Hertz, I'm down to only 2 milliwatts. So for one thing, the passband would be between where I'm at 5 milliwatts or half power. So I'm outside the passband right now. So somebody could ask you, how many dBs down are you? So if you're right at the passband edges, you're 3 dBs down. So how many dBs down am I at 2 milliwatts? So this is what you do. You calculate 10 log of power out over power in. Both of these are in milliwatts. And you calculate that on your calculator. And I don't have my calculator in front of me, so I will just use a Windows calculator and I will calculate it. Let me get my calculator. And look, I'm in programmer mode. Let's put it in scientific mode. You'll need it in scientific mode. So 2 divided by 10 equals 0.2, and I want to take the log of it. So there's my log key, log of it. And the definition is 10 times log of it. So times 10 equals, and it says I'm 6.9 dBs down from the maximum. So that's my example. It says minus 6.9 dBs down. And when you get used to working in dBs, that has a lot of meaning to you. But dBs take a little while to get used to. So different filters have different shapes. Some filters, passband filters, are very steep and narrow, and some passband filters are kind of wide like this, and wide and broad and not so steep and narrow. And each one has a different bandwidth. So my blue filter here has one bandwidth that's more narrow than the red filter or the green filter is. The green filter here is the widest and broadest, and it has the widest bandwidth. So there's a measurement of how good a filter is, and it's called the quality factor with a Q, and the quality factor is related to the bandwidth. So a very high quality filter has very steep sides right here, so that they're actually called the sidewalls of the filter. So a very high quality filter has steep sidewalls, and quality is related to the resonant frequency and the bandwidth both. So the quality factor Q right here, actually we can derive out what the definition of the quality factor is. The Q equals the resonant frequency divided by the bandwidth. So something that has a very small bandwidth will have a very high Q factor. The Q factor will be very big, and that's a high quality filter. Steep and sharp and narrow, that's a high quality filter. It's actually how sharp the sides are is what makes it the quality filter. So that's the definition of the Q, and Q also relates it also relates to this ratio of XL divided by R within the filter. So you can derive the Q that way too for our particular filter that we're studying right now. So sometimes you'll see a Q number, and a higher Q number is better when it talks about how well a circuit performs, or a filter performs. Okay, so let's put an example. What is the 3D bandwidth of this filter? So this problem is actually a little bit tricky because it brings out the point that an inductor is not a resistance-free device, because it's a coil of wire that's wound up, and there's a lot of wire right there, and it adds up to some amount of resistance. So this example put in the fact that my inductor has a winding resistance. RW is a winding resistance. So you have to be careful of that, because you want to make sure that you are using the total resistance when you calculate the 3D bandwidth of this filter. So our total, because we have a winding resistance included, our total is actually the RW plus the R. So that's 50 ohms plus 51 ohms, which is 101 ohms. So that's what our total is, but yet we're only taking the output here across the 51 ohm resistor. So the fact that this is here is going to make my filter perform a little less ideally, but we'll see how that goes in a moment. So let's find what the resonant frequency is for this circuit. It's 1 over 2 pi square root of LC. And I put in my numbers, doesn't have anything to do with R, and I will get 23.2 kHz just by plugging in L and C into the formula. That's the resonant frequency. So I want the 3 dB bandwidth, so I can get that by by getting the quality factor, because we have this Q equals F resonant over bandwidth, and we are trying to find the bandwidth, but we also know that Q equals XL over R. So we can find Q, we have resonant frequency, that means we can find the bandwidth. That looks like a good thing. So Q equals XL over R total, because I have to include the full total resistance right there, which actually lowers the quality factor. If I only had to do the 51 ohm resistor, I would be dividing by a smaller number and my quality factor would be better, but I have to divide by the total resistance that the circuit sees in there, and that makes my quality factor be a little bit worse. So I have L here. Oh, looks like I have to find XL still. So XL equals 2 pi FL, which equals 2 times pi times my resonant frequency, which was 23.2 k ohms, times L, which is 10 millihenries. Watch my units there, and I will get XL equals 1.46 k ohms. So now I have XL 1.46 k ohms divided by R total. I better watch my units, so it's 0.101 k ohms, and then I get that the Q factor is 14.5, and it has no units. So it's a ratio of ohms to ohms, or k ohms to k ohms. Q has no units whatsoever. So that's the Q factor. And then the bandwidth, I can use the formula, comes from the resonant frequency divided by Q. See, I took this and I just rearranged it, right? I did the algebra. Resonant frequency is 23.2 kHz divided by 14.5, no units, and I get that the bandwidth is 1.6 kHz. So I can expect for this circuit, it'll have a peak somewhere here at 23.2 kHz, and then V out or I out, whichever one I want to look at it, whichever way I want to look at it, is going to get less on each side of the resonant frequency. And the pass band here to here, the half power points to 3 dB bandwidth, is going to be 1.6 kHz wide. And beyond 23.2 plus 1 point k, ooh, is that a half? I think that's a half. I think it's 1 point plus or minus, the bandwidth is going to be actually the F low is going to be 23.2 kHz minus bandwidth. So this is total bandwidth. So it's minus 1.6 kHz divided by 2, right? And then the high frequency cutoff point, as we say, the high frequency, the cutoff frequency will be 23.2 kHz plus 1.6 kHz divided by 2, because the bandwidth is 1.6 kHz. Okay. So that's what happens. You get a passband filter if you take the output across the resistor. But what if you take the output across the inductor-capacitor pair? So now I'm taking the output here. Do you remember when we did an RC circuit? If I had V in, and I had an R, and I had a C, and I took the output across the capacitor, then it was a low-pass filter. But if I did V in, and then it was a C and an R, and if I took the output here across the resistor, it was a high-pass filter. But the interesting, even though the circuit's the same and the AC signal V in is still the same AC signal V in, AC signal V in, still the same. So what you see is that this voltage plus this voltage this relationship is maintained for the circuit. So if VR is the output and it's at a maximum because we're doing a high-pass filter, if we're at some frequency where this is a maximum, this voltage will be a minimum. But it depends on which component you're looking at, whether you have a high-pass filter or a low-pass filter. So the same thing kind of applies with an RLC filter. If you take the output across the resistor, you get a high-pass, a band-pass filter. You get something where V out looks like this. Something is passed as a function of frequency. But if this is at a maximum across the resistor, then this must be at a minimum across this pair. So this is across the resistor. So R is the output. But if L and C are the output, the opposite thing kind of occurs. So V out where it's across LC, this is V out where it's across R. V out where it's across LC looks something like this. It's actually quite the opposite, because this voltage plus this voltage, this voltage plus this voltage, or this voltage plus this voltage, all ends up still having to obey this relationship that V out or V in, V source, equals VR squared plus VLC squared. So we have to maintain that relationship at all times. It depends. So you can look at the output across the resistor and then you have a passband filter. But if you look at the output across the L and the C, you end up having what's called a band stop filter, also called a notch filter. So this is a band stop. Your book calls it a band stop filter because it's stopping a band of frequencies from getting through. But it's often called, in industry, it's also called a notch filter, because it's like a notch in the spectrum. So that's a notch filter. It has a stop band, whereas the pass band had a pass band. The calculations are all the same. So we can find a resonant frequency. We can find the output. We can find the output voltage at the resonant frequency and the bandwidth for this particular circuit. Okay, so I think that's our last example for this lecture. So we will go ahead and do it for this circuit. Get my pen here. So they said it's a resonant circuit, so that means XC must equal XL. But let's find out what that resonant frequency is. We will need that. The resonant frequency is 1 over 2 pi square root of LC, because when I find the resonant frequency, then I can find the XL and the XCs. So I plug in my numbers, 1 over 2 pi square root of 0.01 microfarads times 15 millifarads. Make sure you fix your units right there, and you will get 13 kilohertz. That's the resonant frequency. From there I can find out that XL is 2 pi FL, so it's 2 pi times 13 kilohertz times 15 millihenries. I watch my metric units and I will get 1.22 k ohms. So let's see, find the output voltage at the resonant frequency. At the resonant frequency, okay, so we have a winding resistance right here. At the resonant frequency, the current is at a maximum, at FR. The current is at a maximum, and it is I equals V over R, which will equal 100 millivolts divided by R, the total resistance of the circuit, but we have a winding resistance plus this one, so it's going to be divided by 47 plus 30 ohms. And so we find out what that current is. It's 100 millivolts divided by 77 ohms. But the output voltage is a little tricky here because the voltage across this capacitor and the voltage across this inductor are canceling each other out at resonance. And they're saying to take this output voltage across these 2 points, but VC and VL are canceling each other out. So if this winding resistance wasn't here, Vout would be 0. But there is a winding resistance of 30 ohms, so Vout really equals, it's a voltage divider, 30 over 30 plus 47 times Vn. It's really a voltage divider. Yes, so if you do that, then you will get that Vout is 39 millivolts. So if I didn't have this winding resistance right here, Vout would be 0. This is a stop band filter, so Vout looks like this as a function of frequency. So at the resonant frequency, instead of Vout going to 0, Vout really goes to the minimum voltage of 39 millivolts. So then I found, did I find XL? I found XL. So now I can find Q. Q equals XL over R. Is it R that's the output, or is it the total R? It has to be the total R because that lowers the Q of the circuit. So XL was 1.22 k ohms divided by R. R was 77 ohms, and I get the Q of being 15.9, better Q than our last circuit. And there are no units, so it's unit less. And then we can find bandwidth. Bandwidth of the stop band in this case is FR over Q, and that equals resonant frequency (13 kHz). Oh, by the way, your book has a mistake on this. 13 kHz divided by 15.9, and that comes out to be, calculator, 13 kHz divided by 15.9 equals 800. I get 800.817 kHz, so it equals 817 hertz. So let me point out a little typo in your book. Your book, this is on page 603. This example is on page 603. Your book messed up there and didn't put 13 kHz in there. They put the totally wrong number right there. But that's on page 603. They put 1.22 k ohms, which was the XL value there, but then they put the right answer here, so this was a typo in your book. Book error. So it should be 13 kHz right there. I think that's all for this lecture, so we should go to the lab next time, or actually when I get back we'll start the parallel RLC circuit. Very similar to development to how we did parallel RL circuits and parallel RC circuits, but you'd have to find a susceptance total. So that's your sneak preview. Okay, off to the lab.